So it's my pleasure to introduce Deepak Maram today. Deepak is a senior research scientist at Mysten Labs. He got his PhD from Cornell Tech, advised by Ari Juels. He had a lot of prominent works at aerospace labs, like DECO, for example, for decentralized oracles. And in this talk, he's going to talk about his recent project, zkLogin, that's now in deployment in SUI, that allows clients who don't have wallets to get access to blockchain and have an account.
Thank you, Lyra. Thank you for inviting. Okay, so today I'll talk about zkLogin, which is a work which has been live since about 9 months now, that allows people to use their existing accounts to create a blockchain wallet without having to remember another mnemonic or password. A little bit about me. I've broadly worked in the space of Web 2 to Web 3 intersection, trying to bring data to Web 3. This work is about, again, using Web 2 credentials to authenticate to a blockchain. So some more work on interactive authentication. If any of this piques your interest, feel free to chat with me later. I work at Mysten Labs. Most of you know here about SUI, so I'll sort of keep it short and sort of relevant only to this talk. SUI is object-centric. It basically means that it sort of has two types of object, owned and shared object. For owned objects, we can basically skip consensus, and a canonical example is payment. So if I want to send 10 SUI to Hyokim here, and someone else wants to send 10 SUI to someone else, there's no need to order these two transactions in the same log. And we exploit this property to get incredibly high throughput and short latencies for owned object transactions. Coming back to the point of the talk, zkLogin is trying to address a fundamental problem in the space of blockchains, which is that it's very hard for users to get onboarded. And just an example to illustrate this point, if we really count the total number of wallets across all the blockchains today, comes about, let's say, 100 million. But on the other hand, there are billions of Web 2 accounts that people already have that they're using in their day-to-day lives. So it becomes a natural question to ask if we can leverage these billions of accounts to easily onboard onto blockchains. And anyone who has used Web3 kind of knows this problem that I'm speaking about. And MetaMask here is a popular wallet that people use. So if you are a new user, you've never used blockchains, and then you come to the space. So this is something like what you'll experience if you install MetaMask today. You have to first install an extension, which in and itself is a challenge, and it's a drop-off point. And after that, it asks you to remember this big 16-word phrase. And if you can't remember it, it forces you to remember it, and it really makes you actually remember it before you can use the thing. And how many people will actually cross this bridge of installing an extension and remembering a 16-word phrase? Not many. So that speaks to the significant UX hurdles people face in blockchains today. Finally, you get to do your transaction, right? And so the key hypothesis of us here is that mnemonics and keys will definitely not get us mass adoption. If we want these technologies to see the end of the day and we want them to be used by people, we need to come up with new ways of making it easy for users to actually use these systems. A driving factor for us in this, that led us to this work is always imagining the Web 2 alternative. Right? There are millions of websites out there, but people don't remember millions of passwords. Typically, the way people manage the complexity is they have accounts on a few different websites and kind of reuse their accounts across all the different websites, right? And so it again is a sort of a phenomenon we've already gone through in the Web 2 world, and it's almost natural to ask, why can't we do this in blockchains too? I would maybe start with a very naive solution just to kind of highlight what is the simplest thing that we could do here. Now, OAuth is a protocol that is extremely widely supported. Any provider you take uses OAuth, and OAuth is essentially the way, essentially the technology behind allowing users to use a single account on one website to log into different websites. So So a really simple way here would be to combine OAuth with the model of a custodial wallet, right? So imagine you are logging into a website with your Google account. So what would you do? You would just use OAuth, and there would be an interactive protocol between you, Google, and the website you're logging into, at the end of which that website is convinced about your Google identity. Now, for us to build a wallet, this website can, for example, custody your private key. And thanks to that, essentially it can maintain an internal mapping between your Google identity and your private key. And that will allow you to, that will kind of hide all the complexity of key management from the user. And so this is sort of a simple solution that works. And actually, there are many companies that do something like this, or slight variations of this. Now, the motivation for us was to get around this custodial issue. What we would really like is to remove this custodian from the picture and somehow achieve the same user experience as we have here, meaning that as a user, you are never exposed to private keys, while you're able to sign transactions and do everything with a blockchain, but not have the trusted custodian. And there's many motivations for this. You would the simplest of which would be to just remove as many trusted points as you want in your system, just from a security point of view. And so our idea here is to combine OAuth with zero knowledge proofs in an interesting way, where you don't have any more custodians in the picture. The main property we're looking for is non-custodialness, and given that we are using Web2 identity, which may be considered private, depending on the context, privacy becomes an important issue. You don't want to, for example, let's say, post your Google identity information directly on the chain. That would be a big no-no. And of course, the whole point of this exercise was to build a user-friendly wallet, and that sort of drives the design of some of our choices we'll see soon. It turns out that what we need is not exactly OAuth. So what zkLogin bases itself on is an extension of OAuth called OpenID Connect. So it's not as widely used as OAuth 2, but it's still reasonably widely used. And the main difference between OpenID Connect and OAuth 2 is this presence of what is called an ID token. This ID token is basically a bunch of information that is signed by the provider, which in this case would be, let's say, Google, if you're using Google Login, and given to the client. This is basic information that sort of has, let's say, your name, your email, just very, very basic information that Google kind of is attesting to and giving to the client, so that the client can be sure of who is authenticating with, essentially. This is exactly how this ID token looks like. It's sort of base64 encoded JSON. Sort of has three parts to it: a header, a payload, and the signature. And in our experience, this is usually RSA signature. That's what's widely used in practice. Although the standard does specify an alternative using ECDSA. What we've seen in practice is 99% of the providers use RSA. One more, I guess, key point here, we don't really have a lot of flexibility in choosing the payload claims. So the payloads are fairly static. Even the clients, the auth clients, don't have flexibility to ask for different fields. By and large, sometimes there's flexibility to add emails, but that's very rare. By and large, these are very static signatures over very basic information about the user. Now it turns out that this very basic information is enough for our purpose, at least, for that which is authentication. And that's what we will kind of leverage in the rest of the work. And so fundamentally, the idea here is fairly simple. Well, can we just use knowledge of this JWT as an alternative to private key? So can we come up with a signature scheme that leverages knowledge of the JWT in the same way traditional signature schemes leverage a private key to sign things? So that is precisely what we will try to do in the rest of this work. This is a real JWT by Google, so you'll see a little more information here. So there is the ISS, which tells you the name of the provider. AUD is a unique identifier for each client. So if when a website wants to implement OAuth, it will go to Google and register and do all the needful, and then Google issues it a unique client ID, and that's what you see here in the AUD field. Sub is a unique identifier for the user. There is some variance in how providers implement the subject identifiers. Basically, some providers use the same identifier across websites. So if you log into 1,000 different websites, for Google in particular, you will get the same sub. But the AUD will differ because for every website you have a different AUD. But there are other providers like Facebook, for example, I think, which use a different subject identifier for each website you log into. It becomes important as sort of a privacy. The reason they do that is for privacy. As far as zkLogin is concerned, it largely doesn't matter, but it may matter if you're kind of trying to build and do some extensions of it. Nonce is literally the only claim here that the client can control. So the way the protocol works is the client can specify a nonce, and Google will then sign over that nonce. Everything else here is set by the provider. Exp is an expiry time that is set by Google.
Is there a timestamp?
Yeah, so exp here is an expiry time.
So it's pretty short from the issuance?
Yeah, so typically it is set to about an hour.
Oh, okay.
Right, so as I said, sometimes you can ask for other info, but it's very limited, let's say email. And many times we actually wanted to remove some info from there. For example, Facebook was always sending the URL of your profile picture, which like we don't care about, and there was no way to actually remove it. So it's weird, and there's not much control over what actually comes there. So let's get to sort of the main piece here. We have this JWT. You somehow want to now authorize a transaction with it. How do we do that? Typically, in a private key-based signature scheme, you just sign with a private key. Well, there's no such thing here. There is no key or secret the user knows. And so the trick we come up with is to replace nonce, which is sort of the only field we can control here, really, with an ephemeral public key. So it's ephemeral in the sense that the user does not need to remember the corresponding private key for too long. It's fine if they forget it. So what we really do is put an ephemeral public key along with an expiry time into the nonce, and then use the corresponding ephemeral private key to sign transactions. And the idea is that when you actually submit transactions, there will be two parts to it. One with the ephemeral private key signed message, and the other part proving that the corresponding ephemeral public key was in the nonce. That's the basic idea. Now, in theory, there are other ways to do it. Like if you just want to authorize a single transaction, maybe you could put the transaction hash into the nonce. There are potentially other ways, but this is sort of the most extensible way where you can just insert a key pair and kind of reuse the same JWT and for as long as you want. So what we really have here is a certificate over our key. You can really think of this in analogy to a CA, right? So as a user, you're kind of going to the CA, which in this case is Google, and getting a certificate over your key, and later using that key to do whatever you want.
More like a clarification question.
Yep.
You have three components. One is the blockchain, one is this wallet app, and the other is the Google. Right?
Yep.
So Google is trying to authenticate to the wallet, or Google is trying to directly authenticate through the wallet app to the blockchain. Which problem are you looking at?
So we are trying to find a way for a user to use their Google login to authenticate to the blockchain.
Directly to the blockchain. And what is the role of wallet here? It just
more of a facilitator.
Okay.
Yeah. So the wallet would maybe implement the front-end interfaces that will say sign in with Google. But yeah, that is pretty much it. In a way, the whole point of it is to make sure that the wallet isn't a custodian. So the wallet here should not have any information that, let's say, allows it to sign arbitrary transactions.
And how deep is the certificate chain till you get to the public signing key?
So the question is, how deep is the certificate till we get to the signing key of the Google?
Yes.
No, so these are very shallow. So in the sense that Google, the way it works is Google posts its public keys on a publicly known URL. It's just those keys. There is no chaining really. Yeah, so it's just the first layer. I only mentioned CA or certificates as an analogy. There is no chain of certificates really here.
Yeah, but when you present, I guess, the proof about this token back to the blockchain,
Yeah.
together with the signature of the transaction, do you verify the chain of trust?
Yep. So the question is, if we verify the chain of trust when you post this on chain. So the thing we need to verify here is that, so let's say Google posts their keys at google.com/keys, and the way it works in practice is that they rotate it every so often. So we need a way for the chain to know what the current set of keys are, and those can then serve as a basis for doing all of this. So there's multiple ways to do it, but broadly you need an oracle to kind of fetch and post to do this. Yeah. So in SUI we kind of bake it into the protocol level, so the validators themselves act as oracles, but fundamentally you need oracles to get those keys.
Now, with this solution, if Google wants, they can steal most of the money.
If who wants?
Google wants.
So there are some nuances to it, but maybe in some variants of it, yes. I'll come to the nuances. Yeah. So we talked about how to authenticate transactions. The other challenge here is related to privacy. In particular, as I said, there are certain fields here, in particular the subject identifier, that may be sensitive, especially for Google, which uses the same identifier across all websites. You don't want to reveal that publicly. And so the question is, well, how do we derive a unique identifier for the user on a blockchain that we can sort of use to consistently remember them, right? The simple answer would have been just use the sub field, right? That's what Google assigns as the unique identifier. But that is a bit too much from a privacy standpoint, because it kind of links all your off-chain Google activity with your on-chain activity by default. And so the solution we use is to add add sort of a secret that we call a salt to the address derivation. So the identifier we use to represent you on chain is something like this, not exactly this, but anyway, it sort of is a good representation of what we do actually. So it's a hash of, let's say, the provider ID, which is like Google, the wallet ID, which is the wallet you're using, the user ID, your user identifier, and salt. The key points about this address derivation, so this wallet ID here is crucial, because otherwise any random app that you log into with Google can sort of steal your assets, potentially steal your assets. So that's why we put the wallet ID here. Provider ID is just more of again, sort of a similar reason, just to avoid any collisions. I guess coming to salt, the key question is, well, who maintains the salt? There's a couple options here, and I'll talk about it a little later. But given that the main goal of this work is to make sure that users don't remember yet another secret, the main solution we propose is to use sort of a backup service which backs the salt up for the user. And kind of sends it to the user upon relevant authentication. In the context of this work, this will this is usually the app, the wallet provider that can sort of provide the service for the users. That is sort of one main way we consider in terms of how users manage salts. Maybe also worth mentioning, this user ID, as I said, could also be the email address, which enables some interesting applications. Just to mention one, it may be that certain users may, let's say, be okay with revealing their email address. Maybe they're a content creator who want to publicize their work or whatever it is, their reasoning. And so in that case, they could, for example, use an email address here and have no salt. And therefore, then there is sort of a one-to-one mapping between, sort of a public one-to-one mapping between their identity and their, between the two Web 2 and Web 3 identities. So I just want to make the point here that it's not always obvious that we do even need a salt. It's more of a thing we have as an option, and kind of people can then sort of do whatever they prefer to do here.
Salt is just a random seed, random string to
pretty much, yeah.
Then why
so
do you back it up? Why not just maybe ask the user to type in random values, or
so they do need to remember it across invocations, right? So it's a unique identifier that is being used to remember the user. So your address is basically the hash of all of this.
Okay, it's not per signing per
Exactly,
transaction,
it's per user.
Okay.
Consistent, yeah.
Okay.
Yeah, so that's where the challenge comes from. I mean, in theory, the simplest thing here to do would be to just post the JWT directly on chain and validators just verify it, which may work in certain very special cases, meaning that if the JWT doesn't have anything sensitive, and if all parties agree that there is nothing sensitive there, you could, in theory, do that. But that is usually not the case for reasons that I just talked about, meaning that there are either certain claims that are sensitive, or this subject identifier can be sensitive if it is not, if it is the same one across all websites, and so we kind of need a way to hide these things when doing the user login, and that's where we bring in snarks. The statement we prove here is something like this. So you want to prove that you have a JWT that is signed by a Google public key, then verifies certain claims in the JWT. So let's say that the nonce has the right key, and the address is derived from the right claims. In this JSON payload, you care about certain claims, so you kind of need to parse those claims out and prove certain facts about those, and then do some signature verification. As I said before, Google's public key, we are here assuming that Oracle's post that on chain. And so it's a public input to this snark, which gets verified on chain by the real Google public key, but everything else here is private input. You're not revealing anything about the JWT, even the signature, no header, nothing about it is being revealed. Really, the only two public inputs here are Google's public key, the fact that it's Google, and the ephemeral key pair. Sorry, the ephemeral public key. That's how it works at a high level. So just to, I guess, quickly summarize, what we sort of did was took the JWT that is signed by Google, Facebook, whoever, added a salt to derive, to sort of hide the unique identifiers, to hide the sensitive identifiers, but derive a unique identifier for you on chain. Inject a key pair to allow transaction authorization, and then do a zero knowledge proof over it. The thing that you submit on chain has two parts to it: a zero knowledge proof that proves the validity of this JWT, and a signature with an ephemeral key. So that is in a nutshell how zkLogin works. Going a little bit into the snark details, which was Groth16 for now, due to its rich ecosystem of circuits, which allows us to kind of prototype and build things and a fast prover. We are constantly exploring if there are newer systems, proving systems that we could use, and we're definitely open to those. But at least at the time we made the choice, I think Groth16 was sort of a clear winner. But the problem with Groth16 is that these proofs are still slow to generate on end user devices, and so we came up with a hand optimized circuit that tries to minimize the zk computation as much as possible. Even then, in our sort of experiments, it was clear that these proofs were not. It wasn't tenable to run them on user devices. For example, browsers. In our experiments, for example, browsers were crashing when we tried to run it. Not always, but once in a while, probably due to memory requirements. So due to these reasons, we delegate the proving to an untrusted zkP service. So the key point here is that the zkP service is untrusted. So we want to delegate the proof computation, but in a way that the zk service can't, let's say, sign arbitrary transactions. So that's sort of what I mean by untrusted there. Ideally, we also want to do this delegation with privacy, which is a bit of an open question as to how to do that. Because currently, if you look at the witness before, there's a lot of somewhat sensitive things here, like your JWT details or your salt. So all this information will be revealed to the prover. There is somewhat of a privacy issue there. Talking about the circuit itself, let's say the key burden here is really the signature verification. As I said, everything, it uses RSA signatures, which implies that there's a bunch of SHA-2 computation, which takes about 75% of the constraints, and RSA signature verification, which takes about 15%. We spent a good chunk of time trying to optimize everything other than these two, which at the end of the day only took about 11%. I'll talk a little about some of the optimizations we did. But for RSA, we kind of borrowed tricks from existing works, and for SHA-2 we used some circuits that were already out there. The prover itself is based on RapidSnark, which uses some assembly instructions and parallelizes. The RapidSnark is quite fast. I'll have some benchmarks soon. So the key idea here to minimize the ZK computation is to parse the JWT as little as possible. What that means concretely is that we kind of want to avoid, parsing the full JSON. So we assume that the OpenID provider sends valid JSONs and just parse the key value pairs we care about. And for that, we come up with some bit width manipulation tricks to efficiently slice out small strings from a bigger string. I won't go into the details of the tricks here, but basically it allows us to we don't have sort of an asymptotic improvement, but in terms of constants, we have sort of circuits that can slice strings in much more efficient ways. To summarize, the end-to-end zkLogin system looks something like this. We have a user who uses the OpenID provider. So he sort of logs into the OpenID provider, gets the JWT, sends that to the app's front end. So this is, in the case of an extension wallet, it's your extension. In the case of a mobile wallet, it may be your mobile app. So the front end can then use the JWT to fetch the salt from the salt service. So this is the sort of thing that is managed by the app on behalf of the user, and it can also fetch the zero knowledge proof from the zkP service. These two, so these two are basically the external services that are being called and typically managed by the app. And once you get the zero knowledge proof, the app front end can sign a transaction and send it on chain. So we ran some benchmarks to test how fast zkLogin is. As you may expect, the zk service, fetching the zero knowledge proof from the zk service is the expensive operation, which took about 2.78 seconds. I don't have the machine specs here, but it had about 16 cores in it, and more details are definitely in the paper. I guess a couple points here. As I said before, we don't need to fetch a zero knowledge proof for every transaction you're signing. So the real latency perceived by end users differs. So the first time you log into your extension or app, you may experience the 3 seconds delay, but subsequently, as long as the zero knowledge proof is cached in your local memory, it will feel like a normal signature that you're signing. So the latency that users face is kind of different, and they're not really fully exposed to the latency incurred in computing the zero knowledge proof.
What expiry do you have for the ephemeral key?
Yeah, so we have very relaxed expiry. I think the default is 2 days, but I think it can be extended to about 30 days. Yeah.
And after expiry, I need a new.
Exactly. Right. So it's fairly generic. It's fairly loose, and it really depends on where the wallet sits and whether they have access to a secure area where they can put that proof. And not just the proof, you also need to persist the ephemeral private key for whatever time. It's worse on browsers because you don't have any place where you can put this ephemeral private key in a secure place, and so there it may have to be flushed out every session. But it's much better on mobiles, for example.
Ephemeral private key is the sensitive part, right? The proof is okay.
Technically, yes, right. And I guess the transaction confirmation times, it also includes the signature verification. So the signature verification burden is about 2 milliseconds, which is again, about 1 or 2 orders of magnitude more. For now, we haven't faced a problem there, but it is potentially a concern because for validators, you do care about bottlenecks and things like this. The benefit here is that this is completely parallelizable. If I get 1 million zkLogin transactions, I can, in theory, verify them in parallel. But I think for now, it is sort of manageable with a cache to kind of make sure that you don't spend the same time whenever you see the same proof again. and a little bit of parallelization. I think I'll spend a little time talking about various trade-offs in zkLogin. At a protocol level, we don't make any of these choices, whether to use a prover service, whether to generate the proofs locally, how the salts are managed. All of these are details that are that need to be figured out by the app or the wallet that is implementing zkLogin. So if you use a prover service, as I said before, there is a little bit of a privacy leakage in that the prover sees the JWT and the salt, which allows it to link the two identities. The alternative, which is to generate proofs locally, at least today, the problem is that it's too time consuming, but maybe on modern devices, certain modern devices, it works even today. And there is definitely the benefit here. There is also the point here that the proofs can be cached. So even if it takes 10 to 15 seconds today on a user device, that may be fine if it can be cached for a long time. As far as salt is concerned, I talked about the model where the salt is managed by the app. This obviously means that the app now knows your salt and therefore can link your Web2 and Web3 identities. The alternative, which is salt managed by the user, is not as bad because the salt here is not really as sensitive as the mnemonic. Again, it kind of depends on how you perceive it. You asked the question before of whether Google can sign arbitrary transactions, and the answer sort of hinges on how the salt is managed. You could view the salt as a second factor, in which case Google can't sign arbitrarily, because even if Google can sign arbitrary statements, it can't get the salt on behalf of you, and if it can't get the salt, you can't prove the statement and derive the address. So there is an option of using the salt as a literal second factor. There is the option of using the salt as not a second factor, as just for privacy, and you manage it somewhere. So there are all these variations in how people can use the system. And of course, there is also the option of using a multisig. We have multisig support for zkLogin, so you could combine a zkLogin Google with a zkLogin Facebook and create an address that way. So that could also be used to mitigate the risk associated with any single OpenID provider.
Your idea would be that the user uses the hash as an address to receive funds.
The idea for what? Sorry.
If I want to pay you, you give me this hash. And then I send funds to that address?
In general, how would this work? So there's some interesting nuances even there. So one thing that could happen is you create an address for me, because you know my email address, let's say, and you create a new salt. You just create an address freshly out of yourself and just send the salt to me. So from now on, if I can manage the salt myself, then I can access the account you created for me. You send some funds to that address and just send the salt and the address to me. Yeah, so that's one way in which you can create, which is kind of new, and in the sense that you can send funds to someone even before they even know they have an account.
Can you repeat what is the privacy implication of the zkP server? It cannot sign arbitrary transaction. It just
it can see the JWT and the salt, so it can break the unlinkability, and if there's other sensitive details in the JWT, it'll know that. But
not sign transaction.
Exactly, as long as the ephemeral private key is safe. Can't.
And you mentioned you're doing RSA signature verification inside the circuit, and why don't you reveal the hash in the clear,
and do that outside?
Yeah, do the.
Yeah, I think that we did explore that a little, but one of the requirements was to make sure that this whole thing was private from the OpenID provider's perspective. So as an OpenID provider, even they should not be able to link. So this unlinkability that I talk about, so that is even with respect to the OpenID provider. So I'll talk a little about how we integrated with SUI and also what it takes for any blockchain to really integrate something like this. So as I said, we need an oracle to fetch the public keys, and you just need to verify a zero knowledge proof. So it's fairly simple what a blockchain needs. So on SUI, we support it as a first-class primitive in the sense that if you're a user, we don't charge you additional fees or anything for using zkLogin as opposed to something else. And if you're an app, there is sort of a depending on which app you are, there's a couple of options. Obviously wallets can serve it as an alternative, but there is also the interesting option that native apps can just embed zkLogin directly into their website. So if I'm a website and you want to avoid the wallet pop-up, which is sort of so common and sometimes useful, sometimes irritating, what you could do is just have a sign in with Google button there and create an account for the user directly on your website. So there's no need for user to even have a wallet pop-up in your website. So it like in our experience, this option was very useful for things like games where there's too many interactions and kind of people don't want users don't like to see that many wallet pop-ups. I have a demo. Let's see if it works. I think it is working. So this is sort of how it will look if you use Sui wallet today, which is one of the wallets that supports zkLogin. Maybe it's all happening a little too quickly, but essentially what you saw is a user logged in using their Google account. They sent some money to someone else. Click to your Google account, logged in. Sent some Sui, voila. So all it took was like a few seconds, and the reason there wasn't a password ask was that the user was already signed in. There was a session, a Google session running in the browser. If that's why there was no enter your password. But yeah, as you can see, it's all very, very, very smooth. And in our public mainnet, we already support 4 providers: Google, Facebook, Twitch, and Apple, with more in the pipeline. Okay, so to quickly summarize, the key features that zkLogin has is, we have native authentication that is cheap, so users can just use Google login as if they were using, sign in with the private key. Proving your identity is a feature that we haven't touched upon until now. So the point here is that if you are using your email address, you could in theory reveal a part of your email address, like the domain. And you could imagine creating a sort of an account that is controlled by anyone in an organization if you just derived the address from sort of the suffix of the email address, right? So there are, the fact that emails are there in the JWTs allows us to explore some interesting ideas related to identities and playing with identities on blockchains. Embedded, as I said, apps or websites can just embed them directly without even needing for a wallet pop-up. And in terms of authentication, there's all sorts of interesting mixes that are possible here. Combine Google, Facebook, Apple to create a single account. You combine this with mnemonics. One more recent thing we saw was to combine WebAuthn with this. So kind of put the ephemeral key in a WebAuthn. And so the user, and so the key kind of can live for a long time. So there's all sorts of things that are possible here. But I guess last but definitely not the least, one of the key points of all of this is to make these accounts very, very hard to lose. Unlike a mnemonic account, which as many of you might know, many people kind of lose blockchain accounts left and right because it's so hard to remember these mnemonics and maintain these mnemonics, which is complete opposite here. It's kind of very hard to lose your Google or Facebook account because there are so many recovery paths, mature recovery paths embedded into these accounts. To finish the talk, I'll talk a little about some other applications beyond blockchains. So we've already seen a couple of these. You can view zkLogin as a tool that allows anyone to start signing statements without having to have a key pair. You can start signing things and attribute your email address to it. So for example, one cool application I think for this would be for content creators or let's say news publishers or whoever it is to authorize, to sort of sign their content with their email address or a part of their email address depending on the privacy considerations. And we're seeing something like this already for being used by Docker to sign to sign the Docker images. So if you're the owner of a Docker container, they care about the problem of how do you prove that a particular Docker image was sort of who is the author of a particular Docker image and how do we record that. they use a no ZKP variant. In their use case, there's no need for hiding anything in the JWTs, so they kind of just use the JWT directly to sign a Docker image and attach that. But I think it probably has applications for all sorts of content creators and in sort of software transparency and all the other transparency, certificate transparency and other sort of transparency world. Okay, with that I'll finish my talk. I've talked about how to use zero knowledge proofs for authentication, in particular signing in popular providers like Google, Apple, Facebook, and so on to blockchains. Thank you, and I'll take any more questions if there's any.
Do you have any actual concrete numbers of how many people sign up with this service as opposed to kind of like traditional services?
Yeah, so I think, I don't know if I have the comparison numbers. I do know that we have about, I want to say 30 to 40K zkLogin accounts. I don't know what it is compared with the traditional ones. I think some of the, I would say that some of the challenges here relate to the prover and the salt management. As an app, you kind of need to figure those pieces out before you're able to use zkLogin and provide that to your users. I think we are hopeful that this number will go up. We're seeing sort of services that kind of manage these for the users. So for example, Mysten itself has a service called Enoki, which does a managed prover for other apps. As the ease of development for app developers increases, this can really grow. I think we do have some airdrops where, like, let's say millions of NFTs were dropped to zkLogin accounts. But I think really what are used on chain are, like, let's say 40K.
You mentioned non-custodial at some point. How is that enforced, or how do you even define that? Also, was this always a goal? I feel like I've seen previous versions where that wasn't mentioned.
No, I think so, yeah.
But what does it actually mean? Maybe you could break it down.
I am no legal scholar, and this term really is a legal term. So we can try to put our technical hats and put some meaning to the word. But I just want to say that
Sure.
This is
stipulated.
Whether we call it non-custodial or not is not the determinant for what is considered non-custodial from a legal lens. I mean, the argument for it being called non-custodial is something like this. Yeah. So there's who controls the account. Assume, I guess, in some variants the answer differs. But let's say the default variant of it, you could argue that Google can sign arbitrary things and therefore control accounts. But on the flip side, it is, I would say, a lot more equivalent to you storing your private key in a Google Drive. Does that make Google a custodian? In theory, yes. But in practice, I would not call that a custodial wallet either, because Google doesn't know that you are storing your private key there. Google built a service, which is a storage service. You put your private key there. I view zkLogin in that lens, in that Google has a service it is offering, and we are using it to sign transactions. That doesn't necessarily make Google a custodian. I hope that sort of gives the answer. Of course, from a technical perspective, Google can, in theory, act maliciously and sign, if that's your definition of what a custodial wallet is.
So I guess, like, you didn't design it any differently to make it non-custodial. There's not like a guardrail or something. You can use it for any application on chain, I guess.
Exactly. No, I mean, I think we've designed it in a way that there is no service that can sort of unilaterally sign transactions for a user, right? So we have designed it intentionally to be non-custodial.
I guess that makes sense. But I mean, I guess you said Google doesn't know that you're using it for this purpose, but don't they? Don't you have like an ID that, when you make the request, that they see and that they know it's for this service and not for some other use of their OAuth? Like, they treat it the same as anything else, but there is there is a token there that kind of maps it to that it's being used for zkLogin. That
Yeah,
they could
no, I mean, I
probably
didn't mean that
figure it out.
it's invisible to Google. I only meant...
It's not really invisible. I would say it's like transparent. Like they don't
Yeah,
have to implement
exactly.
anything special, but they also they could very easily map requests to this application if they wanted to, right?
Yeah. No, they can. Yeah, so it's. I didn't mean that we're trying to do it in a way where everything is hidden from Google. I just meant that we're using a service that they offer in a way that sort of seems to make them a custodian, but it also feels wrong to call them a custodian because they haven't built the service for that.
Outsourcing the approving to like a server that sees the private witness doesn't break any of the security assumptions in the paper.
Right, so it doesn't because the prover service does not see the ephemeral private key, and that's why it can't sign anything.
How much higher are the fees if you use this account versus?
There's no difference. Temporarily, at least, there's no difference. Thank you.